When an attacker breaches a network, they rarely stay at the entry point. They move laterally, hopping from an external IP to a web server, then to a database, and finally to a domain controller. This sequential movement across isolated segments is known as island hopping. During each jump, the adversary often uses legitimate protocols and administrative tools, appearing to localized firewalls as standard authorized traffic. Traditional intrusion detection systems fail to catch this because they focus on localized data. They scan for specific snippets of malicious code or known semantic signatures, which prevents them from seeing the global pattern of the intrusion. Advanced behavioral tools also have a significant weakness. They rely on historical baselines. If an attacker uses a zero-day exploit or a new variation of a known technique, they can move through the network without triggering any established alarms. Relying on semantic meaning or pattern matching leaves gaps in coverage. When a sophisticated attacker navigates a segmented topology using native tools, they remain invisible to systems that only look for what they've seen before. The SGI Cybersecurity System takes a different path. It moves away from analyzing the semantic payload and focuses entirely on the structure of the traffic. Instead of traditional analysis, SGI models all network traffic as an evolving 256-dimensional field, treating the flow of data as a dynamic geometric system. The system doesn't search for malicious code. Instead, it attempts to integrate the geometry of the network traffic into its own internal mathematical structure. The model detects an attack by measuring its own structural inability to process the incoming data. By translating network traffic into pure math, the system identifies threats through a measurable collapse in field coherence. To process traffic, the system uses thought coordinate, or TC space, translating raw network data into geometry. First, source IPs and port numbers become vectors in dimensions 0 through 9. Next, structural metadata, protocol types, payload sizes, and TCP flags map into dimensions 10 through 39. This process removes semantic context. The system is no longer looking at a message or command. It is looking at a set of structural perturbations. Reducing packets to this 64-dimensional structure prevents attackers from hiding malicious intent inside benign-looking payloads. The system only sees the shape of the data, not the text. The created 64-dimensional vector is injected as a disruption into the larger 256-dimensional SGI field. When the system first starts, it enters a genesis phase. For the first 1,000 packets, it operates in an ungated learning mode to understand the environment. Repeated patterns of normal traffic carve stable attractor basins into the field. These basins represent the network's normal geometric topology. SGI monitors a metric called coherence, or C. This value represents how well a new incoming vector aligns with the established attractor basins. Under normal conditions, coherence remains high, typically between 0.8 and 1.0. This indicates the system is able to structurally accommodate the incoming traffic. In this test of a lateral attack, we see coherence holding steady at 0.8 during normal operations. That changes the moment a 5-hop attack begins. Network segments are isolated by design. A web server is not supposed to have the same structural profile as a database or an admin controller. When an attacker traverses these segments in sequence, they force the algorithm to jump between structurally incompatible basins. The field is hit by irreconcilable geometric forces, causing the coherence metric to drop sharply below 0.5. The SGI algorithm identifies the disjointed topological path forced upon it by the attacker as a mathematical failure to converge. To ensure accuracy, the system requires 3 conditions for an alert. The first is that the coherence must fall below 0.4. Second, the curvature derivative must be negative, proving a sustained decline. Finally, coupling coherence, S sub C, must drop below 0.3, mathematically proving the traffic is incompatible with established basins. If these 3 conditions are met for 5 consecutive packets, the system generates a structured JSON alert detailing the structural collapse. This triple condition lock ensures that alerts are triggered by sustained structural impossibility, not by momentary fluctuations or packet noise. To prevent an attacker from corrupting the system's baseline, SGI uses an ethical alignment gate layer, represented by the parameter omega.
When coherence collapses, the evolution rate of the field slows down. During an attack, the system's learning process essentially grinds to a halt. Because the system stops evolving when it is confused, an attacker cannot poison the model by slowly feeding it anomalous data to expand the baseline. This addresses a major flaw in many machine learning tools, which can be manipulated over time until they accept malicious behavior as normal. This creates a system that inherently stops learning when its internal coherence fails, relying on mathematical limits rather than manual administration. SGI changes the core objective of detection. Instead of recognizing what an attack looks like, the system measures its own failure to integrate the traffic. Because network isolation is a physical reality of the infrastructure, lateral island hopping must produce structural incompatibility. This means lateral movement triggers a predictable structural incompatibility that the system catches without needing any pre-training data. Effective defense against zero-day threats doesn't require a larger database of malicious signatures. It requires a system that understands the geometry of normal operations and responds immediately when those mathematical rules are broken.